welcome to my talk. My name is Markus Winklberger. I'm from the Institute of Structural Lightweight Design at the JQ in Linz. Today I will talk about double shear lugs, which are very common connecting elements in aircraft because they are really easy to remove at maintenance. They act, for example, as pivots, so they avoid the introduction of bending moments into the surrounding structure, and they can be used as joints on control surfaces, or they are used. However, such connections are highly sensitive to fatigue failure due to high stress concentrations, for example, or because of threat and corrosion. As you can see on the pictures here, there have been some incidences in the last years, and so to improve the safety of aircraft, the crack has to be detected before failure, and this is done by monitoring, or should be done by monitoring the structure online and during operation. This is often referred to as structural health monitoring. In this talk, we are talking about the electromechanical impedance method. The method I present here is based on a published paper in 2021, and the method overview is here in these 3 points. First, there is an identification of resonance frequencies which are highly sensitive to cracks in a critical crack initiation location. Then detect the crack and also sometimes localize it by monitoring these crack-sensitive frequency peaks, and it is also possible to estimate the crack length by first identifying in a model-based approach the crack sensitivities. This is depicted here in the graph. You can see here the frequency shift and the crack length, and they are related in a quadratic way. And the sensitivity is negative, as you can see here, for example. So if a crack is growing, the frequency is decreasing, the resonance frequency is decreasing. This talk now extends this published paper by 2 additional geometries, and also the validation of the crack size estimation by multiple experiments. The geometry in blue here, it looks, yeah, it's blue, is the one which is already published, and the 2 shapes on the right side are lugs which are now new investigated. The upper one, the green one, is a tapered lug, and the straight lug. For all of these geometries, a sensor, or let's say a sensor and an actor, is placed on the similar position here, as you can see here in this sketch, in a distance from the lug hole XP. And this sensor is used to actuate the vibration. It uses actor to introduce the vibration and also to measure the frequency response. Constant parameters for all lug geometries are the outside radius and the inside hole diameter, and as already said, the sensor position. So the first step of the method is to identify crack-sensitive frequencies. This is done with a numerical simulation in Abacus. Therefore, we assume the crack position at 90 degrees to the lug position, and multiple crack lengths starting from 0, which is the pristine structure, so no crack, and then in steps of 0.5 millimeters up to 3 millimeters. This crack was modeled in Abacus with a seam functionality to model idleless cracks, so they have no gaps, just the multiplication of the nodes in this region here. These are through cracks, straight through cracks here. Also, the chamfers, some chamfers at the geometry are neglected, and the results we obtain from this model in a steady state frequency analysis are mean major principal stresses in this yellow region here, around the crack, plus minus 10 degree, around 90 degree, and the conductance of the sensor upper surface. So to identify the crack-sensitive resonance frequencies, as already told you, the mean major principal stress is calculated. This is the average of the major principal stress here in this region, and here you can see the results for the straight lug from 50 to 250 kilohertz, and it is assumed that this spectrum element is highly sensitive to the crack initiation and growth for cracks which are initiating in this region. Therefore, the 10 largest frequency peaks are taken, and also frequency bands around these highest frequency peaks are chosen for more detailed investigation. On the next slide, you will see now the frequency band of this resonance frequency for the conductance, so not anymore the mean major principal stress sigma 1 bar, but for the conductance obtained for the sensor upper surface. It's an electrical signal, and there you can see not only one simulation, but actually there are 7 simulations for the uncracked structure and also for structures with increasing crack size. And you can already see that the resonance frequencies are decreasing. From these simulations, we are interested in the frequency peak positions, so the resonance frequency peaks. And so to get more accurate results, the finite element results are interpolated to better get the correct frequency peak position. If we now have the peak positions of all frequency simulations for all geometries with all crack lengths, we can now build and find peak trajectories starting from the pristine structure. And there I used an algorithm by Timothy Gerber from a paper in 2015. And on these slides, you can see now the trajectories for the straight and for the tapered lug, plotted from the frequency shift, again over the crack length. And there you can see from the pristine structure the frequency shift is decreasing because this is a negative axis here. And in these two plots, only the lines or trajectories are plotted, which has a small deviation between the fit of the quadratic trend here with a parameter lambda, and the fit is checked or compared with a correlation factor CCD smaller than 0.03. From these simulations now, the crack sensitivity is saved, as well as the pristine frequency. For the previous frequency band, I took this again. You can see that there was found a quadratic trend. So if we go back, this is this frequency trajectory, peak trajectory, with a sensitivity of minus 77.5 approximately hertz per square millimeter at the pristine frequency as around about 77 kilohertz. Having now identified the crank sensitivity and pristine frequencies for the simulation, we can now step to the measurements to estimate the crack length there. Therefore, I use this measurement setup. The laptop sequentially measures the identified frequency ranges, the 10 different frequency ranges using the impedance analyzer, and the specimens are put on a form pad to avoid any damping and so on. To get some variation for the pristine measurements, I changed the position in 4 different ways. So there's there's a lateral position, standing, and then I made again a flat measurement, but in other direction, only to get the idea on the error which is coming in only from measurement not from the crack. So the next measurements are with an artificially introduced crack. I therefore used a simple scroll saw, introduced the crack at 90 degrees, or also for similar as for the simulations in a step size of 0.5 millimeters. And after every cut into the structure, I measured it with, I measured the crack length with optical microscope to have next to the nominal crack length, the real crack length of the specimen for each measurement. And after each crack length enlargement, I measured the conductance again, and the results. So there's again the similar for the simulation, the frequency spectra for every crack length or for every measurement actually, and out of this frequency spectra, I get the trajectories, which are plotted here, and these trajectories are only the ones who are associated with the pristine frequencies of the simulation. So this is only the frequency trajectories which are close to the frequencies of the simulation. There are actually much more, but to have a clearer picture and to estimate the crack, they are enough. And with the previously identified crack sensitivities, it's now possible to estimate the crack length with the given or with the measured frequency shift. On this slide, you already see that the 4 pristine measurements, so the measurements without any crack, has a small deviation here. So there's a small frequency shift coming from measurement errors or for some additional damping or something else. And this is also done for the estimation, which comes on the next slide. Here again is the trajectory which is associated with the one I showed you before. This is the results for the crack estimation, crack length estimation for the straight lug. As already told you, the crack estimation is done with the measured frequency shift delta F divided by the sensitivity of the crack identified from some simulation results and the square root out of it. In this graph you see again the first 4 measurements, the mean estimated crack length is very small, and after the 4th measurements the crack length increases. However, there is a quite big scatter, and the mean estimated crack length is overestimated by approximately 0.5 to 1 millimeter compared to the blue line, which is the existing crack length. These pentagrams, it's hardly to see on this screen. These pentagrams again are the trajectory previously shown. Similar results are obtained for the tapered lug. Here the scatter is not as big as for the straight lug, and the overestimation is a little bit smaller. Again, the pristine measurements indicate that there's some deviation in crack length, but it's much smaller than the smallest introduced artificial crack. So to summarize my talk, the first step was to identify in a model-based way the crack-sensitive frequencies using mean major principal stresses in a special area where the crack is assumed to be. Then the peak trajectories are found and corresponding crack sensitivities are calculated. Subsequently, the step 3 uses then measurements to get the trajectories of the component in the test, and using this frequency shifts of the measurement, we can calculate and estimate the crack length of the part. To conclude, there was a clear indication of crack growth by tracking these crack-sensitive resonance frequencies, and the crack length estimation is in both cases, I showed you, conservative with the current methodology, so it's always bigger than the real crack length. And have to note that this method, you saw in the previous pictures that there was a form pad which was used so that the part can vibrate in a free way, so that if there's additional damping, for example by clamping or by press-fitted bearings, which are inside the, it's already the last slide, inside the lug hole, the method is strongly influenced, and because the resonance frequencies are strongly influenced, and this is the future research to also get a track estimation, a track length estimation in the clamped way. As you can see here, these were experiments where the specimen was clamped and under fatigue loading with DSC measurement. Okay, thank you for your attention, and I'm happy to answer any questions.